Next is the concept of stack. So stack, as we all already know that the concept of stack means stack is the temporary storage It is the temporary storage area for storing the register content values whenever there is an interrupt or some other disturbance to the microprocessor. So this is used to store all the temporary values in a this is used to store all the temporary register values. So this is the purpose of stack. And it works on LIFO basis, that is lost in first out basis, and it makes use of three registers such as base pointer, stack pointer and stack segment. So these are all the various types of registers used for or used by this stack area. So this base pointer, it contains the offset address to the So this base pointer points or it contains the offset within the code segment, and the stack pointer contains the offset within the stack segment. So this is the segment where actually all the temporary storage happens. So this is the introduction to stack. Now let us discuss about the stack structure. Now let us discuss about the stack structure. So this is the stack structure of 8086 microprocessor, and this part refers to the allowed stack area. Whenever the processor wants to access the stack area, it is using that stack segment value, register value and the stack pointer. So this is the offset address value. So this offset address value refers to the displacement value from the base address of the stack segment. So for example, the stack segment value is 500H and the stack pointer value is 2500H. Next, using these two values, that is these two logical segment address values, we can calculate the physical stack top address value as 52500H. So the calculation is followed. So the calculation of stack top address is as follows. So the given stack segment is 500H and the given stack pointer value is 2500H. So these are all the logical address. Using this logical address, now we have to calculate the physical stack top address, that is 500, and you have to add another 0 or left shift 4 bits to the stack segment register value, and now add this stack pointer value. So you get the 5-digit physical stack top address value as 52500H. So this is the physical stack top address calculation. It means that whenever you want to access the data present in the stack area, first the processor will find out the stack segment value. After that, it will find the stack pointer value. From these two values, it will calculate the physical stack top address value. So it is the exact location where the data has to be placed or retrieved from if the memory is the stack memory. So this is called stack structure of 8086 microprocessor. Next is the operations of stack, that is push operation and pop operation. We know that push operation means inserting a value into the stack area, and pop means retrieving a data from the stack area. So inserting means whenever you push a data into a stack memory location, the stack pointer will decremented by 2. Whereas whenever you retrieve a value from the stack area, the stack pointer will be incremented by 2. whenever you want to push a value, for example, push AX. Suppose you want to execute this instruction, push AX. It means that AH contains a higher bit value and AL contains the lower bit value. For example, the value of AH is 50 and AL is 20, and you want to push this value into a stack memory location. Then consider this as a stack area and assume that the value of the stack values are filled in this order, that is from the highest offset address value to the lowest address value. So in this order the stack value gets filled. Suppose that if the stack pointer points to the physical top address values 52055 and it contains the value 35, it means that, so this is the most recently or last added item in the stack segment value. It means that this address is already occupied, so that will be pointed by stack pointer. Now if you want to execute this instruction, push AX. So if you execute this instruction, first this lower order value, that is 20, will be pushed onto the stack first. So when this value is pushed into the stack pointer will be decremented by 1. Next, it pushes the higher order bit 50 into the stack. Now this value is pushed into the stack, then the stack pointer will be decremented by another 1, that is it points to the memory location 52053. Now this address becomes the stack pointer address. So from 52055 it is decremented to 52053 address, that is stack pointer is decremented by 2 whenever a push operation is executed over the stack area. Now the stack pointer point to this address and it means that the value 50 is the most recently or lastly added item to the stack segment. So whenever this process continues and all the stack offset values get filled and it reaches the topmost value, that is 000, and then there is a no space, then the condition occurs is called as stack overflow. If the value gets filled up to 000, then there will be no space in the stack area and the condition is called as stack overflow. So this is called push operation. And when you consider the pop operation, it's similarly assume the stack area in this direction, that is from bottom to top, means now the stack pointer is pointing to this location 52053, 54, 55, etc. In 53 it contains the value 50, in 54 it contains the value 20, and in 55 it contains the value 35, and etc. And the stack pointer is pointing to 52053. And if you execute this instruction pop CX, then your processor will identify this memory location 52053 because the stack pointer is currently pointing to this location. So whenever a pop instruction is executed, the processor directly identifies the stack pointer location and retrieves this value, that is 50, and it is loaded to the lower order register of CX, that is CL. It contains 50. Now the stack pointer is incremented by 1 and points to this address 52054. Now it contains the value 20, higher order bit value 20. Now this value is also retrieved to CH and with the value 20. Now this becomes empty and this becomes empty. So now the stack pointer again increments by 1 and points to this location 52055. Now it means that there are no other values in the above area and the only item, and the recently added item will be 35. So this is the topmost value in the stack and it will be pointed by the stack pointer. Now the stack pointer location is 52055. It means that it is the top value of the stack. So this is how a push and pop operations are executed using stack. So whenever you consider the stack with two roles, so you can consider the stack with two reasons. You can consider or you can identify the usage of stack with two reasons, that is with stack and without stack. So whenever you can go for this reason, that is with stack, it means that whenever your processor executes program using with the help of stack, then all the register contents values will be stored in terms of any interrupt calls. That is, there will be no data loss or no useful data will be lost during the interrupt call function. But whenever there is no concept of stack, then there will be no temporary storage area and there will be loss of data. There will be loss of useful data whenever there is an interrupt call. So that is the only advantage, or that is the main reason for using stack concept in assembly language programming. Next, we will start with the concept of interrupts in 8086 microprocessor. So the term interrupt refers to that whenever a processor is executing a normal set of instructions, first instruction, second instruction, third instruction, and during any Next, we will start with the concept of interrupts. So interrupts refers to Next, we will start with the concept of interrupts. Whenever a microprocessor is executing a normal set of instructions, and if any interrupt request is given by any external device or a peripheral device, then the processor will suspend its current operations and start executing some other set of programs. They are called as interrupt service routine. So this is the concept of interrupt. So schematically we can represent this as, so first instruction executed, second instruction executed, third instruction executed, and in the fourth instruction there is a call instruction. So it is a type of interrupt to the processor. So your processor will all the register contents to the stack, temporary storage area, and it will start executing a new set of programs called as interrupt service routine. And at the end of every interrupt service routine, there will be a return function. Whenever this return instruction is interpreted, then the processor will return to its normal position where it is suspended its normal operation and start executing its normal set of program. So this is how an interrupt sequence is executed. For example, this is a normal program, then interrupt occurs. So this is an interrupt service routine, returns to the main program, then interrupt occurs, then it is interrupt service routine and it returns to the main program. So this is how an interrupt sequence occurs. In 8086 microprocessor, the two pins responsible for handling interrupt request are NMI pin and INTR pin. So this is a non-maskable interrupt pin and this is maskable interrupt pin. We know the difference that non-maskable interrupt means whenever an interrupt request is given via this pin NMI, then the interrupt cannot be delayed or rejected for any reason. But if it is a maskable interrupt, that is, if any maskable interrupt is given via this pin INTR, then based on the status of the processor can delay or reject the interrupt request. So this is the difference between NMI and maskable INTR pin. So these are all the two pins used for receiving interrupts in 8086 microprocessor. Next we will discuss about the types of interrupts. The two types of interrupts are external interrupt and internal interrupt. From the name itself, we can infer that external interrupt means, so these are all the interrupts given by any externally connected devices, peripheral devices. But internal interrupt means these interrupts can be generated internally whenever a program is executing by the processor itself. So this is the difference between internal interrupt and external interrupt. So example for external interrupts are mouse click and then co-processor interrupt and the keyboard stroke or example for external interrupt, whereas internal interrupts example are divide by zero error, exception handling. So these are some of the arithmetic error. So these are some of the examples of internal interrupts. Next is the interrupt handling process. Next is the interrupt handling process in 8086 processor. Next is the interrupt handling process in 8086 processor. So there are certain steps while handling the interrupt request in 8086 processor. Now let us start with the first assumption that if there is any interrupt request given to 8086 processor through NMI or INTR pin. So if any interrupt request is received as soon as the processor, so whenever this processor receives this interrupt request via NMI or INTR pin, the processor completes all its current execution. So the processor completes all its current execution. And if the type of interrupt request given is trap or divide by zero or NMI, then the processor acknowledges via INTA pin immediately to the corresponding interrupt request device. And if it is an interrupt request given via INTR pin, then the processor checks the status of IF flag. If IF flag is set, that is it equal to 1, then interrupt acknowledgement is given. If it is not set, then INTA, that is interrupt acknowledgement is not given. So this is the first sequence, that is identification of interrupts. To summarize this identification process, first an interrupt request will be given via NMI or INTR pin to the processor. If it is an NMI or trap or divide by zero, then the processor sends interrupt acknowledgement immediately. But if it is an INTR request, then the processor will check for the status of the IF flag. If the flag is set, then interrupt acknowledgement is given. If IF flag is reset, then interrupt acknowledgement is not given. So this is the first sequence. In the next sequence, the CPU computes the vector address using the vector address calculation table. So vector address is computed. After computing this vector address, then the processor will store all the CS and IP content into stack area along with the PSW, that is program status word. So this is the second sequence, that is the backup sequence. It is called the backup sequence using stack. And in the third sequence, based on the vector address calculated, that is it is the address of the ISR, that is interrupt service routine, that is program control will transfer from the main execution to this corresponding interrupt service routine address that is given using vector address. Then execution of ISR happens, and at the end of every ISR there will be an instruction called IRET. So it means that interrupt return. So IRET instruction is executed and the processor continues back to its original normal position by popping up all the values from the stack and retrieving its in original register positions. Finally, the main program execution continues. So this is the 3 sequences where an interrupt is handled in 8086 processor. So first sequence is identification of interrupts, second sequence is the backup of register content value, that is CS and IP values along with program status word into stack, and vector address is calculated. And in the third sequence, based on the vector address calculated, the program control will shifted to the corresponding address and the corresponding ISR is executed from that location, and at the end of every ISR there will be IRET instruction. Whenever a microprocessor executes this IRET instruction, the ISR is completed and the program control is shifted to the main program by retrieving all the content is from the stack. So this is the concept of interrupt handling process in 8086 processor. Next is the concept of vector address calculation. Next is the concept of vector address calculation. So in order to calculate the vector address, first we have to know about the concept of interrupt vector table. So this interrupt vector table is inbuilt in the processor memory starting in the code segment value from 000H. First 1024 bytes of this memory location are occupied by the processor to store this interrupt vector table. So the total size of interrupt vector table is 1024 bytes. So the total types of interrupts available in 8086 are 256, and for each type of interrupt it requires 4 bytes of addresses. So totally 256 into 4, that is equal to 1024 bytes will be entirely occupied. Suppose if the processor wants to calculate the vector address of INT04H type. So this is the fourth type of interrupt, that is 04H. Then first it will have to compute the CS value and the IP value. So this CS value and IP value. So first the IP value is computed using the formula n into 4. So here the n value is 04 into 4, that is equal to 16. So this is the decimal value, and when you convert it into hexadecimal value, the corresponding IP value will be 0010H. Then CS will be calculated as IP plus 2. So CS is equal to 0012H. So this is the corresponding code segment value and this is the corresponding IP value. So this is the procedure to calculate the vector address for any given type. So the formula to calculate IP is n into 4 and to calculate CS is IP plus 2. So for all the 256 types of interrupts, this formula can be used to calculate the vector address, and based on this address calculation, the processor will start executing the interrupt service routine stored in this interrupt vector table addresses. Next is the concept of nested interrupts. So nested interrupt, we all know that the term nested refers to one within another. So the concept of nested interrupts also similar. So main program executes, interrupt comes, then ISR1 executes, interrupt comes, ISR2 executes, then interrupt comes, then ISR3 executes. So after the completion of ISR3, ISR2 will be executed, and the after the completion of ISR2, then ISR1 continues, and after completion of ISR1, then the main program continues. So since one interrupt occurs within another interrupt as a sequence, then this concept is called as nested interrupts. Next, another small concept that have to be discussed in this unit is the concept of macros. So as we all know, the term macros in the procedural C language, that it is a term that is used to describe the set of repeatedly executing instructions. So next we have to discuss about the concept of macros, and the term macros refers to macro instructions. So these macro instructions are the one repeatedly executing instructions in a program, in an assembly language program. So the set of repeatedly executing instructions in the assembly language program are combined under a macro name, and whenever this set of instructions have to be used in the program, then instead of writing the instructions again and again, simply the processor will use the macro name to replace the instructions. So this is the concept or advantage of using macros. So syntax for defining a macro is macro name, that is the user name, macro is the keyword, and here it is the program. Then it should end with the keyword end m. So this is the syntax for writing or defining a macro, that is macro name. For example, you can say it as MSG, and it is the keyword macro, and the set of repeated instructions should be given here. For example, move b comma a, move bx comma ax, inx h, inx d. So if we want to replace these instructions, or if you want to write down these three instructions again and again in a program, these three instructions can be combined under a macro name message. And whenever you want to use these three instructions, instead of writing these three instructions, you simply use this word or use this macro message in the program. These instructions will get replaced. So this is the concept of macros. Macros can be compared to a subroutine program or a function calling in the procedural language, but there are certain differentiations is that macro inserts the complete set of instructions in the place wherever the macro name is encountered. But in subroutine programs or in subroutine working, a function call is made. That means that program control is shifted from one location to another location. But here it is not possible. In macro, there is no transfer of control from one location to the another location of the program. It just simply insert the code in the position of the macro name. But here the control is shifted from one position to another position. So advantages of this macro are execution time is lesser. Here the disadvantages is, since there is a transfer of control, execution time will be larger. The disadvantages of macro is, since the code is inserted again and again during the execution process, the exe file become lengthier or larger. So the advantage here is that exe file will be smaller because the function call is made. So this is the comparison between macro and subroutine. So like nested interrupt concept, we can use nested macros also. That is, macro within another macro can be defined. So this is the concept of macros in assembly language programming. So far in the third unit, we have discussed about the concept of assembly language programming and the various types of stack concepts, interrupt concepts and macros.